morning. Please be seated. I open this public meeting of the College of Deans of the Vrije Universiteit Amsterdam for a PhD ceremony in the Faculty of Science by affirming that from our Christian origins to the present day, we practice science with a sense of wonder and inspired by fundamental values. Prior to his examination, I invite the candidate to give a brief overview of the research on which his dissertation is based. The floor is yours.
Thank you. Thank you. Dear Rector, dear audience, thank you for attending my defense. So I would like to give you a brief overview of the work that I did during my PhD. So when we think about describing or communicating what we know about the world, language is perhaps the most natural representation that we can think of. Language is a very powerful tool for communicating what we know, but it's also very complex, and it can contain a lot of ambiguity and variations in style and in vocabulary. It turns out that in many cases, we can represent what we know about the world simply as a connection between two entities. And if we take such a view, we can represent our knowledge using what we call a knowledge graph. A knowledge graph is a collection of objects or entities that are connected via links that represent some kind of relation. So here we have an example of a knowledge graph that describes Gabriel Garcia Marquez and some of the novels that he wrote. But we can also use knowledge graphs to describe information about countries and also about their exports. This kind of representation of knowledge can be easily processed by computers, and it allows us to answer questions such as, what are countries that export coffee? We can also use knowledge graphs together with methods of machine learning to try to discover patterns in our knowledge. So after analyzing a large knowledge graph, these methods could discover some patterns related to countries and what kind of exports they have, depending on their geographical location. And this can be useful also if we want to go beyond the information that is explicit in the graph. So if we ask, for example, what does Colombia export? The graph here only tells us that Colombia exports coffee. But we could also notice that sugar is also likely to be an export of Colombia, just as Brazil, because both countries are in South America and because both export coffee. So these are the kinds of patterns that we can find in knowledge graphs and that I investigate in my thesis. So in my thesis, I investigate the problem of finding methods that help us discover these kinds of patterns in knowledge graphs. So I start by noticing that many of these methods of machine learning over knowledge graphs proceed by looking at one pair of entities at a time. So they would look at one pair, then they would move on to the next one, and so on. And this is a good idea because we can quickly traverse the graph in this way. So algorithms are fast. But the problem is that this kind of approach might miss interesting patterns that can occur when we look at more complex groups of patterns that we call subgraphs. So subgraphs are smaller parts of the graphs that contain more than two entities. And one of the key research questions that I investigated in my thesis is how can computers discover complex patterns? So I start by introducing a method that we call MPQE. So MPQE starts by looking at the graph and then extracting small subgraphs from it of different sizes. We then take these subgraphs and then we hide some data from them. And then we optimize a neural network to try to predict what was this data that was hidden from the subgraphs. What we find is that with enough of these subgraphs, the neural network can learn to correctly predict the data that has been hidden. What this means is that now we can go with MPQE from answering simple questions such as what does Colombia export to answering complex questions such as what do both Brazil and Colombia export. And what's also interesting it is that with this kind of neural network, we can go beyond what is explicit in the graph into what is likely. So now we can also say that Colombia is likely to export sugar. Now, if I wanted to be honest, I should also say that MPQE can be costly because in order for it to perform well, we need to generate millions of subgraphs. So what this means is that the cost of running this algorithm can increase by a lot. We address this in CQD, which is short for complex query decomposition. Complex query decomposition makes the observation that we can take a small subgraph that represents some query and then decompose it into its parts, into smaller parts. And then we pass these small parts to a neural network that predicts simply a link between two entities. What this means is that we no longer need a large data set of subgraphs of different sizes. We only need a small data set of links between two entities. And by doing this, we manage to be much more efficient in terms of the amount of data that we need to train these systems. So in particular, we go from a data set that contains about 60 million subgraphs down to 1 million subgraphs. So this makes it much easier to basically execute this algorithm in practice. So these are some ways in which we can apply machine learning methods by looking at subgraphs in a graph and then to try to discover patterns with them. But then many of these methods look at the graph simply as a collection of objects that are connected with links. But entities in knowledge graphs might also have more rich information associated with them. For example, textual descriptions. So we can describe a person with a short textual description or also a commodity like coffee. So a second key research question that I investigate in my thesis is how can we incorporate all this information into methods for machine learning in knowledge graphs? I introduced BLP, which is basically a method that trains a neural network to encode the description of an entity in a knowledge graph, and then use this to predict links with other entities. And what we find is that we can particularly do this well for what we call new entities or entities that don't have any other connections yet in the graph. And then in the last part of my thesis, I note that, well, textual descriptions are indeed useful for example, predicting links between entities in this graph. But there might be also other kinds of representations that are more suitable for other kinds of entities, such as molecules. So if we want to add the caffeine molecule into our knowledge graph, we know that we can represent molecules with their molecular structure. So I introduced BioBLP, which is a method for learning from knowledge graphs where entity attributes can be of different kinds, such as text for when we want to describe a person or a disease. We have also a neural network for molecules and also another one for proteins. And we use all these different encodings to predict links between entities in the graph. An interesting finding from this work is that we find that this kind of approach is particularly useful for less connected entities. So entities in the graph that don't have many incoming or outgoing connections. And what we find is that if we incorporate attribute data, we can compensate for the fact that there's not many connections in the graph. And in this way, improve the predictions that we make over these entities. So in my thesis, I present methods for exploiting subgraphs and attributes into methods for machine learning on knowledge graphs. And we find that this allows us to do a number of interesting things like answering queries over incomplete graphs, also add new edges to them or add new entities to them. And finally, we also look into how to do this in a way that is efficient. So using less data so that these algorithms are not as costly to run. Thank you.
Thank you for your presentation. I would now like to hear whether the candidate is prepared to defend his thesis.
Rector, on your authority and as authorized by the College of Deans and according to the decision of the Dean of the Faculty of Science, I am prepared to defend my thesis entitled Exploiting Subgraphs and Attributes for Representation Learning on Knowledge Graphs in order to obtain the degree of Doctor of Philosophy.
Okay, thank you. I'd like to start the examination now. We have 3 examiners locally here in the room and 2 other examiners who will be joining us via a Zoom link. Before we start, I'd like to thank all 5 of you for the time and effort that you've put into evaluating the thesis. A rigorous review is at the heart of the scientific endeavor that we're all involved in, and we appreciate the time that this takes. I would like to start the questioning by inviting Dr. Osaka, who is Associate Professor in the Department of Informatics at the University of Oslo, to open the examination.
On the authority of the rector and by virtue of my right, I'm going to make you some questions. And before that, I would like to make you some comments about your thesis work. You have presented a lot of important results, new results, and they are important in artificial intelligence and in knowledge representation. And those results were published in top conferences such as NeurIPS. So you have just given us an overview of some of your results using complex query answering in knowledge graph embeddings, and also how to use some other attributes, how to use textual information, and how to apply it in some domains related to life sciences. And these are all relevant topics. So my first question is related to theoretical properties. So I was wondering whether you have considered theoretical properties that would be relevant for answering complex queries in knowledge graph embeddings. What would those be? And if you would have an idea of which ones would be satisfied or not, and that's all totally up to you. Where do you want to go with the answer?
Right. Learn the point. Thank you for the kind words and for the questions. Definitely, I think if we look at the thesis, the main focus is on empirical results. But of course, theoretical connections are very important. And I think I can answer this question by referring to 2 chapters in particular. So I will start with MPQE, so in chapter 2. In MPQE, we approached the idea of answering queries over a graph by using a neural network to embed the query, so to convert it into a vector, and then answer the queries using nearest neighbor search. So I think in this case, the theoretical properties of MPQE are very tied to this neural network that is used to encode the query. And I think we saw an example earlier today in the talks that graph neural networks can have limited expressivity. And when it comes to comparing 2 graphs, even if they are isomorphic, a GNN can say that they are not. And this could be a problem for query answering, because it means that we could find 2 queries that are different, but a GNN treats them as the same. So I think it's important to look into this issue and try to find if perhaps this is one of the ways in which we could improve MPQE by finding architectures for encoding the GNN that have better guarantees on distinguishing these kinds of graphs. And the second thing I want to refer to in terms of theoretical results is in our work on complex query answering. In CQD, we find that we can reuse link prediction methods to answer complex queries. And I think this is it's very interesting in the sense that there have been years, decades of research in link prediction methods that have to try to make them more expressive and more powerful. So all the theoretical guarantees that we can get from them then can transfer to the complex query answering setting. So I think what this means is maybe we can limit ourselves. This might be a bit controversial, but maybe we can limit ourselves to just trying to capture pairwise relationships between entities and guarantee that in the embedding space we can preserve logical constraints. And then all these properties will transfer to the complex query answering scenario when we combine scores with T-norms and T-core-norms as we did with CQD.
So, dear candidate, coming back to the beginning of your answer, you talked about the structure of the queries and the difficulty of GNNs or distinguishing those structures. And in particular, it is known, for instance, that if you look into regular graphs, then they have this, there's these challenges. But in your thesis, you consider during the evaluation queries that have some particular structure, in particular structure that is tree-shaped. Do you consider, are you aware of results regarding this difficulty of GNNs, whether they are applicable to tree-shaped queries?
Right. Yeah, I'm not particularly aware of these kinds of connections with tree-shaped queries, so I don't think I can elaborate on that.
And regarding the theoretical properties, for instance, let's say one of them one could think of for your setting is you may have some queries that are more complex, let's say have more conjuncts than others. In database theory, we have this notion of query containment. And so one particular property that could make sense is it the case that if you have a more specific query, would it be the case that all the results that you get there would also transfer to when you have a simpler query?
So when you say a more specific query, is it a query with more constraints, or how would you define this?
For instance, a query with more constraints. So a query with, let's say, 3 atoms, and then a query with 2 atoms, and those 2 atoms coincide with, let's say it's a substructure when you consider this mapping that you are already familiar with between the query and the structure.
Okay. Yes, I think if we think of, for example, CQD, in CQD we use T-norms and T-core norms, which are simple functions that we can use to combine scores, which are like degrees of truth, or yeah, let's say degrees of truth. And then these functions have some simple properties. So if we keep combining them, for example, if we get a query with more constraints, that would mean that we combine more scores. And we know that these functions are basically either convex or concave, which means that the score is going to keep decreasing, for example. So that would be one way of directly modeling these kinds of constraints. And I'm also aware of other works that are connected to MPQE that were developed in our lab, where there's some theoretical results actually on how adding constraints to a query and then maintaining these in the architecture of a neural network basically constrains the set of answers that we get. So thus effectively modeling the fact that we're constraining the query further.
And another property that one could think is, for instance, you have your knowledge graph, and you would make a query to a knowledge graph and have some answers. And in your thesis, one of the motivations for querying the embeddings is that you would not just want to have the answers from the knowledge graph, but also answers that would be likely to be true. So that hints to the idea that perhaps you would like to have all the answers that then are 100% considering the information present is correct, plus additional ones. So is it the case, or do you have any idea whether the method would satisfy such a property to maintain all the, I mean, you described in your work more than one strategy, but you comment on that, whether it would preserve the answers in the knowledge graph or not.
Okay, thanks for the question. I think we do have some guarantees of this that come from the fundamental idea of maximum likelihood estimation. I think this is at the core what's happening whenever we train methods for link prediction, because we are optimizing explicitly for the edges that we observe in the graph to have a high score compared to those that are not observed in the graph. But at the same time, it's not the same as when we use maximum likelihood estimation to train a classifier when we have positive and negative data, because in a knowledge graph, most of the time, we only have positive data. So we have to fabricate negatives by random sampling, which means that these kinds of guarantees that we get from maximum likelihood estimation might not hold, in the sense that we don't know if the observed edges will always be ranked up high all the time.
When considering, let's say, the top K,
If you could give us a short question and a very short question and an even shorter answer, that would be very nice.
okay, just then I still have a lot of questions, but okay, I'll just finish with that then. Recall the top K and can you, I mean, it is still related to this question about the preserving the answers of the knowledge graph or not. Do you think it would depend on the K?
The top K is CQD.
Yeah.
Okay, I think the short answer is we could potentially modify K based on the known edges for intermediate variables. I think that would be my first thought.
Thank you.
Okay, thank you very much. I hope that you've had the chance to ask your core questions. In the highly unlikely event that we run long on time, then we'll come back to you for the rest of your questions. But before we get to that point, I would like to invite colleague Niepert, who is professor of machine learning in the computer science department at the University of Stuttgart, to continue with the questioning. Dr. Niepert, welcome from Stuttgart to here in Amsterdam.
Thank you. And on the authority of the rector and by virtue of my right, I want to first say thank you for a very good presentation and summary of your work. Also, I think that, yeah, your work is actually very influential. So I know of many of my PhD students and PhD students of other groups who were quite influenced by this work that you published. Yeah, so where you also won the Best Paper Award for it, I clear, yeah, essentially using simple link predictor for complex query answering. So I think this was a very, very influential work, and of course is a central part also of your thesis. So very impressive, and also I want to not repeat too much the positive feedback you already got, but yeah, I think it's a very influential work, and yeah, I want to commend you for a fantastic dissertation. And now I also want to ask you some questions. And the first question is about this method that I just mentioned, which yeah, uses essentially the idea that you can use the scores that you get from simple link prediction methods and then put them together to answer complex queries. Could you maybe outline very briefly and also describe the challenges of how you actually do this putting together? So how do you use these individual scores and place them together to answer a complex query?
Okay, learned opponent, thank you for the kind words and for your question. So in order to use CQD, what we need is a good method for predicting links between entities, and then a way to map them into an interval between 0 and 1 that represents a degree of truth. Once we do this mapping, we can combine them with T-norms and T-core norms that model logical operators such as AND and OR operators. And this is where the first challenge arises, because fuzzy logics is a huge field, it's a very old field, and it has developed all these functions like t-quanorms and t-norms with the underlying assumption that these scores are faithful reflections of our knowledge about the truth. And this is not necessarily the case with link prediction methods. So we have some heuristics or hacks to try to map some scores into this interval between 0 and 1. But then in the end, we sort of have to cross our fingers and hope that their scores are what we call calibrated. But of course, there have been works that have shown that scores from link prediction models are not calibrated. And there is also work on actually improving this, on getting calibrated link prediction methods. So one of my hopes is that once we get this either via some kind of training procedure or by incorporating background knowledge, when we can get calibrated link prediction scores, then we will definitely see some benefits when using them in conjunction with t-norms and t-quanorms.
Okay, thank you. Then so the idea that you're following in your work is that you take these individual scores and you're formulating an optimization problem essentially, right?
Right.
I was wondering, and then there are different ways to solve this, right? And you use continuous optimization, but also combinatorial optimization. But I was kind of wondering, have you also thought about or analyzed kind of generally the properties of this optimization problem? So how difficult is it to solve? So for instance, if I use continuous optimization, will I actually be guaranteed to get the optimal solution? So these types of things. Have you thought about this, and what are your general thoughts on this?
Right. Thanks for the question. I definitely thought about this, and this is something I think we spent a couple of weeks with our collaborators on this same question, because when we were working, particularly in the continuous optimization version of CQD, which uses basically gradient descent to find the best embeddings for the intermediate variables, we were thinking it would be much nicer if, for example, we could compute an analytical solution to this problem. And we know that we can do this for the case of simple link prediction, because many link prediction methods are essentially linear functions. So we can find the global optimum. But then as soon as we start combining multiple scores with t-norms and then t-quanorms, then the landscape ceases to be either convex or concave. So then it's not an easy problem. So we did try to find ways to like have some guarantees on the solution, but the best we could do is just use gradient descent, and then we could see that this optimum, even if it's not guaranteed to be a global one, was good enough to answer complex queries.
Mm-hmm. And so then is it also true that it's difficult in some cases to disentangle the reasons why maybe your method might not work in particular situations? Because it could be that the initial scores are already quite poor that you're getting from the link predictor. But it could also be that even though the scores are actually quite good, that this kind of optimization problem is not solved yet exactly, essentially. So have you also investigated this to some extent and looked into this?
Yes, thanks for the question. It is true. There are different factors that can influence the performance of CQD. And I think a natural progression from this work is trying to indeed disentangle these factors. So you mentioned the scores and then also the optimization problem. I think we did look into the issue of scores with the follow-up work to CQD, which is CQD-A. So CQD-A learns a function for adapting the scores. And this is motivated by this issue that the scores from link prediction models are not calibrated. So we can then learn a very small and efficient function to adapt it to complex query answering. And what we find is that this indeed improves performance. I think this answers the question that calibrating the scores can be an issue in CQD and can be addressed with this adaptation. And what remains is the optimization problem. I think that's something we can still think about better ways of finding this optimum for the intermediate variables in CQD.
Okay, yeah, thank you very much for this good answer. I also wanted to, and please also interrupt me if I'm asking too long. I think I have a couple more minutes.
Not to worry.
Okay, great. Yeah, so I also wanted to ask a question about the link prediction with text attributes, which I find quite intriguing. And I was kind of wondering, because we also kind of looked into this in the past, and you know, there's in the knowledge graphs, there are kind of a mishmash of different types of nodes, right? So some are nodes representing classes, yeah, or concepts, you know, something like love or yeah, so very general things. And in some cases, we have named entities. So we have, yeah, Albert Einstein, these types of things. So I was kind of wondering when you looked at incorporating text attributes, and especially also kind of in this inductive setting that you mentioned, where you don't yet have maybe a lot of links, did you also kind of analyze, like maybe according to different types of nodes, how well this actually works, and how also how difficult it is actually to make it work, depending on what type of nodes we're actually looking at?
Right. That is true. That is something that we observed in the data that we used for BOP, which is the method you're referring to. Because in this work, we use knowledge graphs like Freebase that can contain heterogeneous types, so people, but also locations, movies. So it's true that we can find this heterogeneity in the graph. And when it comes to the influence of this in the performance of the model, I think this could be an issue, especially if we were to rely on heuristics to try to turn these descriptions into something usable for link prediction. But in BLP, what we do is to do this process in an end-to-end way. Well, actually, I think there's two aspects here. So one is that we rely on pre-trained language models. So these are language models that have observed a vast amount of data that talks about all different kinds of entities. So in a way, I think it's primed for this heterogeneity that we can find in knowledge graphs. And then second, we train it in an end-to-end way. So we're not just reusing the features from this model, but also fine-tuning it for the link prediction task. And I think these are ways of addressing the fact that there can be all different kinds of entities. But then, yeah, to answer the question, we didn't look into like specific kinds of types for this work, but we did it for the next one, which is called BioBLP. In this case, we looked at the performance over different kinds of types, which was actually pretty small. We had proteins, molecules, and diseases, I think also genes. So, and even then we did see a performance that varied depending on the type and also on the relation type. I think there's some figures in the appendix, if I remember correctly, that describe all these differences in performance. So it's true, we observe this in our experiments.
Mm-hmm.
Okay,
Great.
I would like to stop the questioning from Professor Niepert at this point. And again, if we have extra time, which I doubt, we will put you on the candidate list for a second round. But first, the first round to colleague Hertz, who is professor in the Department of Computer Science at the Universiteit Antwerpen. Professor Hertz, welcome, and we look forward to your questions.
Okay, thank you. And on the authority of the rector and by virtue of my rights, I want to ask you some questions and go into discussion with you about your thesis. But before doing that, I also want to compliment you on your work. I mean, as was mentioned before, it's of very high quality. You have already kind of a couple of very influential publications with lots of citations. And also you work like award winner of this prestigious ICLR kind of award. So this is all very positive. Unfortunately, that's where the positive news ends. And I would love to go into discussion with you. As you know, I'm coming from the database world. And so database systems and theory have been around for 5 decades with query evaluation methods, algorithms, index structures, systems, multi-billion dollar industry. And if I would start a company where I would promise my clients that I'm not sure about the fact that I will give you back all the answers that you need. Also, I'm not going to promise you that the answer that I give you are going to be correct. I'm also going to only be able to answer very, very simple queries, which I will call complex queries, but they aren't. Why would I invest, or why would I, become your client? Because in your work, basically you're proposing or you're advocating the combination of complex query answering and neural methods in a kind of harmonious way. But from a client perspective and from a database perspective, there is no harmony yet. So can you give me some comments about this positive remark by me?
Yeah. Learned opponent, thanks for the question. I think I also would invest in that company. I think, interestingly, this is a discussion that we had a lot with reviewers. And I think what needs to be very clear is that the goal is not to replace graph databases. Because as you mentioned, they have been around for a very long time. They have been studied a lot, and we have guarantees for them, like really good guarantees. So it wouldn't make sense to just try to replace them with this fancy new toy that we get with AI. I think I would invest in a company where a graph database with such guarantees is available, but where neural methods are used to provide additional insights of patterns that are available in the data. Also, because we know when we observe, for example, real knowledge graphs, we know that even if we have a lot of people invested into building them, like Wikidata, this process of building a knowledge graph takes time and takes effort. So machine learning methods like the ones I describe in my thesis are a way to sort of help with this process to provide or to constrain all the data that is available in the world and present it as a suggestion to humans that then are actually in charge of using this information.
Can I interrupt you, dear candidates? Because what you're telling me is like a general, answer that can be, answers for any type of machine learning. Right? So what are precisely the new insights that you get by approaching this from a neural perspective?
Okay.
And how sure can you be if so suppose I'm becoming your clients and I believe in that you're adding value to my data. So can you give me an example, and how sure can you guarantee me that what you give me is indeed something that I should act on? I should hire new people or spend some money somewhere, buy some products. So
right. Yeah, so what I can try to do is to, for example, if we look at methods for link prediction or query answering, what I can do is to try to show how good these methods are at actually providing answers that were not possible to obtain in the graph before. Because if we take a graph and then we answer some query, we get some set of answers. Mm-hmm. But then that set of answers might be incomplete. So with evaluation methods like the ones we show in the thesis, we actually remove information from the graph, and then we show how neural networks can recover those original answers. And that's something that a graph database wouldn't have been able to do because the data was just not there.
Okay. So then to come back to like a very concrete example, can you give me one example of data that you discovered in any of the knowledge graph experimentally that was not known before or was kind of untrusted, and now it has become part of the, you know, future editions of the knowledge graph?
Right. I don't think in the thesis we discover something that wasn't unknown, because in all cases we focus on or maybe more like the way we set up the training and evaluation is by us manually designing this scenario when we remove edges from the graph, and then we evaluate if the model can recover them.
Mhm.
But in the end, we had a graph that had all this information, so we didn't really discover anything. We just used the graphs as a benchmark. So I cannot claim that we made a breakthrough discovery or anything of the sort. But I think what's interesting is, for example, the benchmarks that we used in the biomedical domain. I think this hints at what's possible when it comes to actually discovering new knowledge, because we have models that learn embeddings of entities that we then use to predict interactions between drugs and proteins, for example, or drugs and drugs, which can be used to, for example, propose drugs for a new kind of treatment.
Okay, right, thanks. So I understand that, so that it's basically like a complementary approach to classical query answering. I'm focusing now mostly on the query answering part in your thesis. But then I'm still left a little bit kind of in the blue in some sense, like you give me answers, but are there any methods for explaining why you give a certain answer back? So I would be happy to, you know, to invest again in your startup company, promising me these things, but then I would be more assured if I would have some, you know, like a technical way to somehow explain why you recommend a certain piece of data, why something should be added to my knowledge base. So is this available? Is
Right.
this part of, can this be followed from the computation, from the way that you construct the neural embeddings?
Yeah, thanks for the question. I think that is indeed a natural question when it comes to using these systems. But the first thing I would wonder is whether you really know what an explanation is for you. The problem is that explainability has been worked on in machine learning for several years as well, and graph neural networks are just one example. And one of the key questions in this works all the time is, what is a good explanation? So for some people, a good explanation is a verbal explanation. For other people, if it's a graph, it's a selection of the edges. So first, we need to start by defining what would be a good explanation for you. And then if we say it's something like a selection of the edges in a graph, then there's indeed methods for this. For example, there is a word called GNN explainer. And in this case, what they do is to select parts of the graph that have maximum mutual information with the prediction that the graph neural network is making. And I think we could transfer this to, for example, the query answering scenario. But I would still be left with this question of whether this is a useful explanation for you or not.
Okay. Do I have time for one?
72 seconds left.
So what about the logic-based explanations? Like, you know, some logical formulas that explain, like, you know, these are the properties that that are matching the formula, and, you know, these are the ones that if I would remove them, for example,
Yeah.
you know, like the answer that I would return would not be returned again by my neural methods. This could be like a counterfactual explanation in some kinds.
Right.
Yeah.
Yeah, this is indeed another kind of these methods for explainability that could be applied. But the question also is, if we use automated methods to come up with these explanations, and then suddenly for a prediction we get a logical formula of 100 lines long, is that still something we want to show to a human? I believe it might be, and it might be more useful than just a prediction out of a black box. But I think it's still an open question, like how to come up with good explanations for these models.
Okay, thank you. Thank you.
As fond as I am of this line of questioning, we have to move on to a questioner number 4, or we have to. I'm very pleased to move on to questioner number 4, colleague Paulheim, who is professor of data science in the School of Business Informatics and Mathematics at the University of Mannheim. It is good afternoon to you, and we look forward to your questions.
On the authority of the rector and by virtue of my right, I'm very happy to get into the discussion about your thesis, dear candidate. But first of all, let me state that I read a lot of papers on embeddings and related topics, and I really enjoyed your thesis because it takes an unusual angle, getting away from this simple triple scoring link prediction to more complex queries. So I really enjoyed that, and congratulations on doing this work. Now getting into some details. You say you do complex query answering, but my feeling is that you're actually just tackling a subset of complex queries. So you might, for example, ask for a list of pairs of countries and their capitals, or of what relates A and B. And none of these seem to be solvable by your approach. So could you, in principle, transfer your approach also to those other types of queries?
Learned opponent, thank you for the kind words and for the question. It is true that we use the adjective complex quite loosely in these works. We simply define it as queries if we look at them in terms of subgraphs, queries containing more than 2 nodes, and that's it. And even then, I think we can still achieve quite some interesting results based on the observation that training neural networks on just a link prediction problem generalizes very well to more complex patterns. And because this motivates the idea that we can combine them into arbitrary patterns. Just when going from the link prediction case to arbitrary patterns, I think this gives us an idea as to how complex we can go with these methods. But we do see some problems as we increase the complexity of these patterns. For example, if we look at path queries, when we go from length 1 to length 2 to length 3, there is a monotonic decrease in performance of these methods. So there is indeed a limit as to the complexity of the queries that we can address with these methods. And in terms of more expressive knowledge graphs, so for example, there's knowledge graphs with additional information on the edges, like hyperrelational knowledge graphs. Luckily, in our group, there has been work on this area as well, where these ideas from complex query answering have been extended to these knowledge graphs. And what we see in these cases is that we need to find a way of mapping this additional construct that we have in models like knowledge graphs with hyperrelations to some kind of embedding.
Let me interrupt here. Let's just stick to this basic knowledge graphs for the moment and ignore this hyperrelational world. Another thing that I came across is that when I looked at the data sets you used for evaluations, actually the majority of the queries does not seem to be complex, right? So most of them are these what you call 1P queries, where I have a subject and predicate and I look for the object, like what does Colombia export? Have you looked at what is the performance of just using the link predictor on these 80% queries, that the neural link predictor you're using anyways?
So you mean looking at the performance of the model on simple link prediction queries?
So if you just look at the 1P queries in your test set and just solve them with complex, and is the performance about the same? Is it exactly the same? Does it boil down to that?
Well, it depends on which chapter we're referring to.
We're referring to chapter 3, the CQD methods.
Okay, then in CQD, the performance should be exactly the same.
Okay.
Because we in that case, the whole method just reduces to complex. So there
So we actually only need the machinery for the remaining 20%. Is that correct?
Exactly. Yeah.
Okay. And as you already mentioned, the knowledge graphs that are out, like Wikidata, for those knowledge graphs, we actually also know what people want to know. So there are query logs. Have you looked into those query logs and tried to find out which portion of these queries your approaches can cover and which portion of these queries are those 1P queries which can be solved by a simple link predictor?
Right. The short answer is no. I know about these query logs. In fact, one of my supervisors mentioned it to me quite several times. Yeah, I think this is something we plan to look into, because I think what's interesting about these query logs is that they give us an idea of what is actually relevant when trying to apply the system in the real world. In terms of complexity, what we do in MPQE, in CQD, all these works is to say, let's look at query graphs with 4 nodes and all possible structures that we can form with them. And then we use that as kind of a benchmark for evaluating the systems. But there is a disconnect between that and what people actually need in the real world. So it would be really interesting to take these query logs and just parse them and try to see how they map to all these benchmarks that we have been using in all these works to try to get a good idea of how relevant they are in practice.
If you didn't start from the real world problem, what then motivated you in doing your work?
Sorry, can you please repeat the question?
Yeah, as you say, yeah, well, in the future, we can look at the real world problems out there. So if it were not the real world problems, what was the motivation of doing that work in the first place?
Right. The motivation was to look at, to bound the size of the queries, because we cannot just experiment with an infinite amount of query structures. So, and I mean, this is also because when we worked on MPQE, there was already some work on query answering. So it was easy for us to compare with these works if we stuck with their data sets. So the motivation is to bound the size of these queries, and then to at least try to experiment with all the different kind of queries that we can get from these say kinds of subgraphs.
Okay, maybe one short question on this MPQE approach again. So one thing you use in there are embeddings for entity types, which you use for these target entities. What do you do in graphs where types are not that present for every entity, or where entities may have multiple types? How do you deal with those situations?
Right. I think that was one of the experiments that we did at some point, and I think the easiest way, or like a natural way to do in this case, is to use a generic kind of embedding for variables. So in that case, we wouldn't distinguish when it comes to initializing the embedding of a node. We don't have the type information, so we just learn some kind of embedding for a variable. But this might not work very well, because then we're not using the same embedding for all types of entities. So the next thing I could try is to use the information that the edges give me, because we know that the identity of a relation like birthplace or exports already tells me something about the type of the head entity or the tail entity. So sure, this may be one way to determine the type, and then learning an embedding for each kind of position at a triple.
Okay, as you say, you've investigated that. What is the impact of the type embeddings compared to just using generic variable embeddings?
Right. Yeah, unfortunately, these experiments are not in the thesis, but we did run them. And what we see is that indeed using the type embeddings results in better performance, because yeah, it's essentially giving the model a better notion of the different kinds of entities that can appear at different places in the query.
And can you quantify better? Is it like a huge jump, or is it a marginal improvement?
It's not a huge jump, but yeah, I don't have the numbers off the top of my head, but it is not significant. That's all
I think I've used up my time, right? Otherwise, I could go on.
I think you have used up your time, but it was an interesting line of questioning, and I'm sure that Professor Hogendorn has no problem donating the 1 minute that you took from his time. But thank you very much. And we appreciate your opportunity to ask the core questions in any case. Last but not least, our own Professor Mark Hogendoorn, who is Professor of Quantitative Data Analytics here in the Computer Science Department at our own VU University. Thank you for the 3-minute walk from your office. I'm afraid that you don't have very much longer to ask questions, but make the best of it.
On the authority of the rector and by virtue of my right, be a candidate. I had a lot of compliments, but I won't speak them out because I only have 5 minutes with you. But it's a great thesis, was a pleasure to read and an important contribution. So thanks a lot for that. Of course, a good thesis gives food for thought and also some questions. And I want to start with some questions related to chapter 5. So going into the biomedical data setting. And actually the first question I had, you already answered in the question by Professor Geerts, namely that you didn't really look at new links that you found that were sort of outside of the, let's say, known knowledge graph already, because you removed some of them. So I was wondering, didn't you take a quick peek to see whether there was something novel that came out where you felt that could be interesting, or didn't you do that at all?
Learned the point, and thank you for the kind words and for the question. Yeah, I unfortunately I did not take a look. I basically look at the benchmarks that we had, which again, as I said before, this is all the things that we know a lot. We know about. I could have just essentially run the method and removed what we know, and then try to interpret that, but that would also require some domain knowledge. And in the biomedical domain, I don't know if I could determine this is really a novel thing and scientists should be looking at this right now.
Okay, so that makes sense. So there were no biomedical people involved or research involved in the work. It was mainly focusing on, can we try to get it to work from a technical perspective?
Right. We did have people in the team with expertise on biomedical data, but indeed the priority there wasn't really to then apply this to generating novel insights. And I think that's probably the next natural step, which is actually using this to make decision.
Right. Okay, so imagine that you were going to do that. So let's look a bit into the future then, where you're going to use your method in that sense. So what do you think these domain experts would need? Would it be you saying, look, I found this link, can you research it? Or could you give some extra context, some explanation that could help them in studying whether this would indeed be an interesting part to pursue?
Right. I think this varies a lot from the people that I have talked about this work. I have discussed this work with doctors, and it's very interesting to see what their perceptions are about the predictions that we get from these models. So some really need some kind of explanation to trust what the models are generating, whereas others are like, literally, they say, I don't care about this prediction. I just want something that then I can verify with my own background knowledge. So I think at minimum, what we can give to these experts is some sort of expectations on the kind of predictions that we get from these models. And then maybe have a conversation with them about what extra things do they need? Do they need an explanation, or are they fine with just taking that?
Okay, thank you. So I think you work at the Amsterdam UMC now, so perhaps it's some avenue worth exploring.
That's
I wanted to continue the line of reasoning within chapter 5 and actually your questioning. Actually, you look at multiple modalities, of course, around this data. But I think each one, at least as far as I understood, has its own embedding. So it's not really sort of a lot of cross-fertilization in an early stage of the different modalities, but it only happens all the way at the end when you already have an embedding. So could there be what are the downsides to this? Of having, let's say, a sort of a late fusion approach in a way, right? Where you have embeddings all the way in the end?
Right. I think the downside of this is that it assumes that we can represent entities of different kinds, like proteins and molecules and diseases. It assumes that we can represent them ultimately with the same embedding space. And I think this is a strong assumption, and it might be one of the reasons why the model is not performing so well. Because on one hand, for example, for diseases, we're trying to encode natural language that describes the disease. And then on the other, we're encoding molecules. So the question is this shared embedding space really a good idea? Or should we maybe try to find like an intermediate representation where each kind of type can have different representations and then try to fuse them?
Okay, thank you.
Now that my defense has ended, I sincerely thank the opponents for the attention they have devoted to my thesis. I now look forward to the decision of the doctorate committee, which will decide whether the degree of Doctor of Philosophy will be granted to me.
I hereby adjourn this public meeting of the College of Deans for private deliberations. Please be seated. I reopen the public meeting. By its duly accorded authority, the doctoral committee grants the degree of Doctor of Philosophy to Daniel Daza Cruz, and the degree of Doctor of Philosophy is granted cum laude, which is a distinction that we give to approximately the top 5% of research in this area. So, oops, sorry. I invite the supervisors and co-supervisors to place their signature on the degree certificate as witness of this deed. I declare in public that in the privacy of the closed meeting, the candidate by his signature stated adherence to the conditions laid down in the provisions of Article 5 of the doctoral regulations of this university regarding the rights and responsibilities in science and society. I would like to invite Professor Paul Groth, appointed by the College of Deans as supervisor, to perform the investiture. During the investiture, I invite the examination committee and other supervisors to stand. The rest may remain seated.
By the virtue of the authority vested in me by the management regulations of the Vrije Universiteit Amsterdam and as supervisor appointed thereto by the College of Deans, I hereby confer on you, Daniel Fernando Daza Cruz, the degree of Doctor of Philosophy, Doctor, together with all rights, privileges, and responsibilities thereto appertaining. In witness thereof, the seal of the university and signatures of the rector and the supervisors have been affixed to the diploma you are about to receive.
Thank you. Please be seated. I would now like to invite Michael Cortez, who is the co-supervisor of this work, to perform the laudatio.
Esteemed committee, dear colleagues, family, friends, dear Daniel. Today we gathered to celebrate a significant milestone in your academic journey. Your defense marks the culmination of years of dedicated research intellectual curiosity, and unwavering perseverance. I first met you when we were still in the WN building, where you shared an office with Emil at that point. Even then, your drive for knowledge was evident as you passionately explained your master thesis work and the foundation of what would later become MPQE. So little did I know that this enthusiastic researcher would embark on a journey that would not only shape his own academic career, but also leave a clear mark on my own and on our research community. Your journey to a PhD was not without its challenges. You navigated the uncertainties and complexities of academic research and even a global pandemic. On top of this, you also survived having 3 academic supervisors, me and Frank at the Learning and Reasoning Group at the Vrije Universiteit, and Paul at the India Lab at the UVA. Yet you remained steadfast, driven by an insatiable curiosity and a relentless work ethic, which made you a cornerstone of the Elsevier Discovery Lab. Your ability to adapt to changing circumstances and your unwavering commitment to excellence have been instrumental to your success. I vividly recall the frantic week leading up to the WebConf submission deadline. With time ticking away and no paper in sight, you, with your characteristic determination, pulled off a remarkable feat. The resulting paper was a testament to your creativity, ingenuity, and ability to work under high pressure. This incident, among many others, highlight your capacity for innovation and your talent for turning challenges into opportunities. Beyond your academic achievements, you're a remarkable individual. You have a passion for travel and a remarkable ability to eat spicy foods. But above all, your willingness to help others, your modesty, and your ability to find joy in the simplest of things make you an inspiring role model. As you embark on the next chapter of your life as a postdoctoral researcher at the Amsterdam UMC, I have no doubt that you will continue to make a significant contribution to the field of artificial intelligence. Daniel, we are honored to have had you and still have the opportunity to work with you. We wish you all the best in the future endeavors. Thank you.
To the congratulations of your supervisors, I gladly add the congratulations of the College of Deans of this university. I found your defense very interesting. I found your presentation very clear. And it is fascinating to know what this kind of work can do. It's also fascinating to know what the limitations are of this work. And both were addressed today. And I understand that you're staying within the VU family at the medical center. And we wish you all of the congratulations and best wishes for a fine career in the future. This PhD ceremony is now completed. Doctor of Philosophy Cruz will lead us out of the hallway. We will assemble at the statue of Abraham Kuyper in the lobby if you'd like to give a quick congratulations. We will all follow him out of the hall. That is to say, we will follow him and you will follow us. I ask you to stand. I close this public meeting of the College of Deans by desiring that our scientific search for truth and wisdom may be beneficial to the world and to humanity.